Hello students, my name is Shashank Shekhar and good evening. So sorry for the being late. So we were doing a crash course on chemistry of 45 days and today we are here on the 8th day. So in the previous class I have ended the chapter chemical bonding. So today we will start the physical chemistry chapter, that is thermodynamics. So today we will deal with only the first law of thermodynamics. So our focus will be mainly on this first law. So first we will deal with the terminologies. So there are many terminologies like say we have a wall, then we have the system, then with the surrounding. So we will study about those things one by one. Okay, so let us start. So first is the system. So what is system? So whenever you carry a reaction, you do it in a beaker or a you can say a test tube. So you do it in a beaker or a test tube. So in that part, the region that is enclosed inside the beaker is called as the system, and anything that is except that beaker is called as surrounding. So suppose we have a beaker here like this. Okay, so we have a beaker here and we are carrying out the reaction in this. Now this part is called as system, where the reaction is taking place. And except this part, all this space around this, including the universe, that is the system, universe minus system, is concluded as surrounding. So all this place is surrounding. And to if you want to define the universe, then it is equals to, so universe is equals to system plus surrounding. So this is the very conceptual thing about system, surrounding and universe. Now you can see that there is a wall. So this is the wall here. So it is separating both the system and the surrounding. So this is the wall. So this is separating the system and the surrounding. So it is defining a boundary between the system and the surrounding, and it is called wall. So wall can be of many types. So we will study those types later on. But before that, let us study what a system. So there are many type of system. So the first one we have is we call it as closed system. So what do you mean by closed system? So in a closed system, it only not allow the means does not allow the exchange of mass as well as heat. So you cannot exchange energy as well as mass with the surrounding. So that kind of system is called a closed system. Then we have the open system, which can exchange both heat and energy, heat and mass. Then we have the isolated system, which can only exchange mass, which cannot exchange mass and energy both. Sorry. So for the closed system, we cannot exchange this energy, but mass we can exchange. Then you have the open system, which can exchange both mass and energy. Then for the isolated, both cannot be exchanged. Okay. So it is wrong written here. System that allows the transfer of energy but not mass. Okay, so yeah, it is right. So a closed system allows the transfer of energy only, but not mass. So let me keep one thing clear here, that whatever the system we will study in thermodynamics, most of this system will be type of, you can say, they will be mostly closed system or isolated system. So in thermodynamics in class for this JEE exam, open system is not considered much more time. So you will not see open system very often. Then we have wall. So I have denoted the wall with the green thing that it separates. It is a imaginary boundary between the system and the surrounding. So wall can be of many types. So first one is a diathermic wall. So it allows the heat transfer between the system and the surrounding. So you will later on see with what is heat, what is work in definition form. But you know what is heat if you study in the 9th 10th also, then heat is something. It is a form of energy, you can say. Then we have the adiabatic wall. So adiabatic wall does not allow the transfer of heat. So if you have an example, so you have a very simple example, that is thermosteel. So it is not a perfect. You cannot say it is ideally that adiabatic wall, but to some extent, means you can say to a very extent, it is able to isolate the system and does not allow the transfer of heat. Then we have the rigid wall. So in rigid wall, we mean that the volume of the system is kept fixed. So suppose you have a piston, then in the rigid wall, those piston cannot move, so it is not functional. Now, while defining a state, so if you want to define a system, a state of a system, then we need various properties like the pressure, the volume, the enthalpy, the internal energy. So you know about these terms. If you have heard it, you must have heard it. If not, then I will make them clear one by one. So you must have heard the term temperature and volume and pressure at least, because they are very common words. So these properties are used to define the state of a system. Now, these properties can be of two types. So first one is extensive property, and second one is intensive property. So what is extensive property? So extensive property are those which depend upon the amount of the substance that you are dealing with. So suppose if you have to define mass, then you have to, of course, it will change with the amount of mass, amount of substance you are taking. So suppose if you are taking something that is in a feast, if you are taking something that can be enclosed in a feast, then suppose it is 500 gram. Now you are taking something that is enclosed in a large tank. Then of course the material is same in both case, but the mass will of course change. So if you want to do, if you want to classify them in a very easy manner, then you can think of it in this way. So suppose I have a container here like this. So this is the container. So I am taking a cuboidal container. So what do? We put a partition in that cuboidal container like this. So suppose this is the partition. So this is the partition we say. Now we have said that initially this boundary is not between these two compartments. Then the pressure, volume and temperature. So initially the pressure, volume and temperature and number of moles. Suppose we take number of moles, and then we have mass. So these are the five properties we are taking. Now suppose we introduce this thing here. So if you put a barrier in the between, the temperature between both of this will be same. So how it will be do? So suppose initially this is this one. Now we put a barrier here. Now what does we say this one as compartment 1 and this one as compartment 2. Now when we put this barrier here, upon putting this barrier, we do not see any difference between the pressure, volume and pressure than temperature. So pressure and temperature does not change, so it is very obvious. So suppose the pressure here is 3 atm, it will be also 3 atm here also. But the volume and the number of moles and the mass will of course change. It is obvious. You know that the volume is dependent upon the amount of substance and also the number of moles, because suppose here in the total compartment there are 10 moles. Now if you put a barrier such that 8 moles goes to this side and 2 moles goes to this side. So after putting the this barrier here, then we have different number of moles on the both sides. Similarly goes for the mass, because number of moles is nothing but mass divided by molar mass. So in this way we can say that finally, so after putting that barrier, pressure, volume, pressure, temperature remain same, while volume, number of moles and mass changes. So this is the thing here. Okay. So in this way we can easily differentiate between extensive and intensive properties. So we can see here many examples are given. So extensive properties are like mass, then volume, then energy. Yes, energy is also dependent, because we know from the formula also. So if you want to look it from a different perspective, then you know that E is equals to mc square. So it's Einstein's formula. So it is easily seen that if you want to calculate the energy, then it is interconvertible to mass also. So if mass is extensive property, then also this energy. Then we have intensive property. So intensive property can be like temperature, pressure, and density. Yes, density. So this is a very so if you want to define it right now, so let me define it. Density. So density is equals to mass per unit volume. Mass per unit volume. Now this both mass and volume are extensive property. You know it, extensive property. Now you can keep this term as general. So you can keep this rule as general, that the ratio of any two extensive property is always an intensive property. So you can keep it this in your mind. That's the ratio of any two extensive property is an intensive property. You can take any two extensive property and divide them. Then you will get that ratio, and that ratio will be always an extensive property. So it is an extensive property. Intensive property, sorry. Intensive property. So these are the definition of extensive and intensive property. Next, we have functions. So you know what is function. So if you are not aware about what is function, let us take a simple example in maths. We can take a simple example in maths, like we have fx is equals to x square plus y plus suppose we have a one variable equation, quadratic equation, 2x plus 1. So this is a kind of function. So this is in mathematics. So this function can also be extensive in state function, path function. Now what do you mean by this? So this is a very definition of function in maths. So why I am telling this in this way? Because many times in exams you are not given the actual function value, but you are given a function, mathematical equation that will define that function. Now function can be of two types. So it can be a state function or a path function. So students, this is a very important thing to notice. So you do not get an easy eye on it, because it will be important in later chapters, means later exercises, where you have to calculate the state function and the path function. And children often get confused that yes sir, the path is given for reversible, and why are you using the formula that is used for irreversible? So the difference lies here between the state function and path function is that, so a state function only depends upon the initial and final position, okay, and does not depend upon the path that we are taking. So this is the main criteria that is used to calculate this thing. So suppose we have something that is for following the so-called, you can say it is following a reversible path, but you are calculating it for irreversible, but the function is a state function. So the value will be same. It will not change along with this thing. Okay, so you should keep in mind this thing, the state function, path function. So it will be used. So if you want, you can have the example of work. So work is a, you can say a path function. It depends upon the path that we are taking. Now, if you want to simply define, this differentiate between this state function, path function, we have a trick. So we will see it later. Now the second one is path function. So what is path function? So path function is something which depends upon the path that we are taking to carry that work out or that process out. So the simple examples are heat and work. Now suppose you are told to see that whether this is a path function or state function. So if you are saying that it is having a delta sign before this function, so suppose we have the delta h or delta u. So we will see these terms later on. So suppose I am taking a general term like delta a or delta b. If you see that delta is used along with it anytime, then it is always a path function. So it is not in a literal sense. So I'm just giving you this, you can say a trick to do this. So if you see in a book, if you see the NCRT, all those functions which have a delta sign before them on the left side will always be a state function. And other than all those will be a path function. So you can decide the state function with this. For path function, you can go to the concepts. Okay. So you can be assured about that. If you see a delta sign before this function in an NCRT book, then it will always be a state function. Okay. So now we will move to types of processes. So if you see a process, so it can happen in many ways. So suppose if you want to go to somewhere, you can go to through many ways like airways, waterways, landways, and various other ways. Similarly, if you want to do a process, so it can be done in various ways. So we will have some that those ways. So we will study those ways one by one. So we will have isothermal, adiabatic, then we will have isobaric, isochoric, and all of those. The first one is isothermal. So what is an isothermal process? So later on we will calculate these functions, or you can say these properties of this processes one by one. So you must keep in mind this processes definition always. So the first one is isothermals, where thermal means heat, or you can say temperature more accurately. So not heat, temperature. And then iso. So the process which is having the same temperature throughout the process is called as isothermal process. Then we have the adiabatic. So adiabatic is that process which is having no exchange of heat between the system and the surrounding. So here we are taking that, yeah, that there is no change in the system, but if you want to define it as a whole, then you can say that there is no heat exchange between the system and the surrounding. Now next we have the isobaric. So what is isobaric process? So in isobaric process, the pressure remains same. So you are doing a reaction such that we are having the isobaric condition. So most of the reaction that we carry out in our labs are isobaric. So suppose means most of this, I mean that we are mostly carrying a reaction in an open vessel, and open vessel means that we are carrying a reaction in 1 atm pressure. So most of this reaction is isobaric. Then we have isochoric. So isochoric means we have the same value of volume throughout this throughout this process. Now, if I ask you that, okay, say me that what kind of wall will you put here so that it will have this isochoric process? Then you have studied about the wall and you know that it is the rigid wall that does so. So rigid wall is such that it does not change, that it does not move up and down or sidewise, so that the volume of that compound can that container can change. So in this way, isochoric process can be used that using the rigid wall. Similarly, if you want to do an adiabatic process, you will need an adiabatic wall, and for the isothermal process, you will need an isothermal wall, or you can say uh, something that is not allowing the exchange of heat, like a thermosteel or a thermo, you can say bottle. Then we have so we have seen the processes on which were based upon the type of condition which we are using. Now we will see that how this process is carried out, and based on that, we will define what is reversible process and irreversible process. So now, for now, we are just seeing the definition of it, of reversible and irreversible process. Then we will see that with the help of work done. So when we will calculate the work done, you will see more clearly what is the difference between this reversible and irreversible process. So in reversible process, the thing happen is what? That we are doing a reaction or a process such that we are moving the process towards means forward in very small steps. So that is, suppose a reaction is happening in 10 seconds. So suppose a reaction is taking part in scales of 1 to 10. Then we are moving it in very small fraction like 10 to the power minus 7 of this 1 to 10 scale. In this way, we are keeping the system in equilibrium at each step we are carrying out. So you do not need to get much into this. So you do not need to get a theoretical aspect into it if you want to do this exam with very well. So if you then you should be only aware about that that in a reversible process, it can return exactly to the same state where we have started. And always you have to take a dx length rather than a delta x. So that is the most important point. So you have to take small intervals, very small intervals, and integrate them to get every function. Whereas in irreversible process, you will take a larger part of the process one at a time, and then you can do it easily. So you will just take the larger part one at a time and get an answer. But in a reversible process, we will take small parts and integrate over this whole process to get that function. So before moving to the this first law, let us study this Zeroth law of thermodynamics. So what does it say? It says that suppose we have a system A, B, and C. Now this B is in equilibrium with A. Similarly, this C is in equilibrium with A. So in this context, we can say that B is in equilibrium with C. So if you want to understand, you can say, simply understand it like this. So suppose you are touching something that is at 30-degree temperature, and you are also at 30-degree temperature, 30 degrees Celsius. So it is X for you. So let us say it X. Now you are saying that, okay, I am in thermal equilibrium with a third body that is also 30 degree. Then of course all of these three will be in the you can say equilibrium with each other. Now the term here arises is equilibrium. So that is about the temperature, that is very straightforward. So when we use the term equilibrium, things get somewhat complicated. So equilibrium can be dynamic, or you can say it can be static. It does not depend upon that. But Zeroth law always follows for this kind of conditions. So dynamic equilibrium means the system is changing with time, but the overall change is not observed by an observer. While in a static one, there is no change in the equilibrium. The system is not changing at all. It is static, means not the pressure is changing, not the volume is changing, or any state function is changing. So in thermal equilibrium, if A and B are in thermal equilibrium, similarly, A and C are in thermal equilibrium, then B and C will also be in thermal equilibrium. So this is the zeroth law of thermodynamics. Then we'll move to work. So what is work? So if you have heard this term in physics also, then work is equals to the distance into the force applied into displacement, that is F dot D, that is F D cos theta. Now in physics, in chemistry, or you can say thermodynamics, we use this formula, that is W minus P del V. So I will not get into its derivation because you must have seen it multiple times that yes, it is minus P delta V. So if you want to say it very quickly, then pressure is equals to force by area, and volume by area gives us that displacement. So it will be force into displacement as well. So in very quick way I can say that. So it is like this. So work is equals to minus pressure which will equal to force by area by delta V. Now delta V by A will be displacement, F dot X. So here you can see that yes, it is only nothing but the formulation of this F dot X into P delta V. And why are we using a negative sign here? So it is just used to keep the sign convection correct. So if a system is doing this something, then a system is, suppose we are applying force on the system and compressing it. Okay, so we are compressing it. Now we are doing work on the system. So the work done should be positive. But since the final state is less and the initial state is more, so final minus initial will be negative. But since we have done work on something, it should be positive. And to keep that convection correct, we have used its negative sign. So minus minus, we get the plus of work done. Okay. Now we will move to the isothermal process. So we have seen earlier that work done. So we have various type of process: isothermal, isobaric, isochoric, and various other processes. Now we'll calculate this work done for different processes. The first one is we are calculating work done in an isothermal process, and not just any isothermal process. We are doing it in for the reversible case. So yeah, I have told it earlier that I will define this reversible and irreversible more clearly when we're calculating the work done. So here you can see that we are moving from one part to another, from one state to another. Suppose this is the initial one, this is the initial one, and this is the final one. Now, when we are moving from initial to final, we are doing it in small steps like this. By which I mean that I am not directly moving this system from here to here, but we are doing it in small steps like dx, we can say. So in case of volume, dv. So dv1, dv2, dv3, and dv4. So in this way, we are moving the volume by small steps such that we do not disturb the equilibrium. So in every step of this process, the system is in equilibrium. So system is in equilibrium here, it is in equilibrium here, and here, and here, and so on. So in this way, we move from V initial to V final. Now, if you want to calculate the work done So suppose this is we are calculating the work done. We know that work done is equals to PdV. Now we are considering for it for a small change in work. So see, we have written it dW. Then for dV1, so I'm writing it dV at a small part. So we are taking a small part of it. Yeah, in this thing here, let me make one thing clear that in this graph, it is shown that this small parts are not equal. But whenever we are using this formula or integrating using like this, then we are considering that okay, we are having say we are having this all parts equal unless and until we do have a function of this dv. Okay, so we will see it later in the next class when we will take examples of it and see it how it happens. Okay, so we take a small variation of this volume for calculating a small work, then that is dw. So dw is equals to pdv. Now since we are calculating it for initial to final, we integrate it from v1 to v2. Say this it as v1 and say this is as v2, or you can say v initial and sorry v final and v initial also. There is no problem in it. Now we integrate it for this. Now you can see here that we have PdV. So we need volume term. So because we do not know that whether the pressure is changing or not, so we are not given any idea about that. But we know that volume is of course changing. So we will replace this P with mu RT by V. So it is the ideal gas law, ideal gas law. Why I'm giving this derivation? So many times you are asked the question that okay, so you are given that PV is equals to this, and you have said that now you calculate this work done for using this equation of gas. So for that reason, I'm giving you the definition. Now we will replace this P by mu RT by V, so it will be dV by V, and integration of dV by V will give ln V. So same thing is written here, it is ln V. Now we are putting the limit it as ln V V1 by V2, all things are same, minus nRT by this. So it will be ln V2 ln V2 minus ln V1. It will be ln V2 by V1. So same thing written here. So we are taking here for V final and V initial. So this is the final equation. So this equation is very important. It will be used multiple times. Now if you want to replace, so suppose we are not given the volume change, but we are given the pressure change. So how you will do it? So we will replace this V final, V initial by P1, P2. So suppose we have a value of given here, that is P1, V1. So we know it from this ideal gas equation. So we are taking the same temperature. So we are taking an isothermal process, of course. So the temperature is same. R is a gas constant, it is same. And I've told earlier that we will calculate mostly for the closed and isolated system. So there will be no change of molecules or moles. So for equal volume and temperature at and R is constant, we can say that P1 V1 is equals to P2 V2, or you can say, so I am replacing this for not getting confused. So I am replacing it with V2. This is V1. Now we can say that V2 by V1 is equals to P1 by P2. So I have replaced this V2 by V1 by P1 by P2. So you can use this formula also to calculate your answer. So many times you are given the pressure condition and not the volume condition. So you will use this formula to calculate the number of the work done in isothermal process. Okay. Now we'll take an isothermal irreversible process. So in what happens in an irreversible process? So we are directly moving from one state to other, and without taking any small steps. So it is like this. So suppose we are given a system that is at a volume of V initial, and we go from Vi to Vf in one step. For that case, it will be calculated in very simple formula using the other formula we have seen earlier also, that it is equals to minus P delta V, where delta V is equals to V final minus V initial. And minus sign is put up here to keep up the sign convection so that we do not get a negative work for doing a work on a system. So whenever you do a work on a system, it is always a positive work. And whenever you are the system is doing the work, then it will be a negative work done. So let me make it clear. Work. So this is the sign convection we use in chemistry, thermodynamics chemistry. Work done by the system is negative. Work done on the system is positive. Now let us move to free expansion. So what is free expansion? So in a free expansion, we do so is that we expand the gas in an area that is large enough so that there is no external pressure on it. So the external pressure for free expansion is zero. So for this case, we are considering this is a special case. We take free expansion that we are expanding a gas in such a volume that such that the external pressure that is applied on the gas while expansion is zero. Now we know from the formula that work done is equals to minus P external delta V. Now P external is zero, so the work done will be also zero. Now if you move to the delta U, so it is found experimentally, or you can say that it is said that while doing so, the change in temperature is also zero. So the change in temperature is also zero. And you will later on see that why this delta U will be zero. So I will define it later. So with a different formula. So since the temperature is zero, this delta U is also zero, and we have this formula that delta U is equals to Q plus W, and therefore we will see this. Okay, so I will make this free expansion more clear in the later section. Then we have the work expansion for the reversible adiabatic process. So next, what is the condition that we are taking a reversible process, which is adiabatic in nature, so there will be no heat exchange between these two things. Okay, so what do we know? That W is equals to delta U minus P dV. Okay, so we have this thing that W is equals to delta U minus P dV. Now we know that delta U is equals to CV dt. Delta U is equals to CV dt. And for P, we replace it by RT by V from the gas equation. Then we will integrate on both sides. So for temperature and for volume, we will put this T here and B here. So we will get it as log T2 by T1. Log T2 by T1, ln T2 by T1 and ln V2 by V1. Now 0.6 whatever 2.303, that is ln is equals to 2.303 log, so 2.303 cancels on both sides, and finally we get this formula, that is log T2 by T1 is equals to minus R by CV log V2 by V1. Then we know that Cp minus Cv is equals to R. We replace this Cp minus Cv, this Cv by this thing, so R by Cv can be written as, so we divide this by Cv. Now Cp by Cv is equals to gamma. Gamma Cv gets cancelled and we get R by Cv. So if you put this here in this thing, R by Cv 1 minus gamma, so we will get this equation. Log T2 by T1 1 minus gamma log V2 by V1. Now we know the this log property that n log A is equals to log A to the power whole n. Now we are doing the same. We are putting this V2 by V1 and here. So it is log whole n. Now we are putting this V2 by V1 as gamma minus 1. Then it is V1 by V2. Why? Because log V2 by V1 is equals to minus log V1 by V2. We know that. Now we take this minus sign outside, that will be gamma minus 1, and it will finally this equation. So we get this equation. Now we again tumble it ups and down. So this is the final formula, that P1 B1 is equals to P2 V2 gamma. Okay. So this is the main equation here, that PV gamma is equals to constant for adiabatic process. Now next, similarly we know that PV gamma is equals to constant. Now we calculate it for T1 T2. We get it as T1 by T2 gamma, P1 by P2 gamma minus 1, P2 by P1 1 minus gamma. Okay, so we get this thing here. Then we can calculate the work done in adiabatic process like this. That work done is equals to NR TF minus TI 1 minus gamma. So if you know this gamma P1, P2, T1, T2, then you can calculate the work done. So this is a work done in adiabatic process. So let us now do a question to calculate the work done in an adiabatic process. So it is given that we are giving the initial temperature T1, that is 300 Kelvin, final temperature T2, that is 200 Kelvin. So these both things are given. So first we'll write the given thing, that is T1 is equal to 300 Kelvin and T2 is equal to 200 Kelvin. Now, next step, we know the formula that R by gamma minus 1 is equals to T1 minus T2. So substituting this, we get as W is equals to R by gamma minus 1, 300 minus 200. Further, we will get it as 100R by gamma minus 1. Therefore, work done will be 100R by gamma minus 1. Now this we will study this gamma in the second chapter, so second lecture. So this gamma, we know that Cp by Cv is equals to gamma. This gamma will change for monatomic gas, for diatomic gas, for triatomic gas. So that is a different thing. We will see it in a different chapter, different slide. Now again, we have a question here. So it says that a sample of an ideal gas undergoes an adiabatic process. If the initial temperature is, so initial temperature is given as 500 Kelvin and the final temperature is 250 Kelvin. Now what is the ratio of initial volume of, to the final volume? So we have to calculate. So what is the ratio of the initial volume to the final volume? So you know the formula, you can use it. So if you see here, the formula is this, that T1 by T2 gamma is equals to P1, P2 by P1 gamma minus 1 minus gamma. So you know all this. So in this way you can calculate it. Now let us move to the next concept. That is work done for a irreversible adiabatic process. So first we have seen for the reversible adiabatic process. Now we'll see it for irreversible. So the thing here is that, so it is a kind of free expansion thing only. So the formula will be used, it will be same. So it is a you can say a free expansion. So it will be W is equals to 0. The volume changes from V1 to V2 against pressure P. Now we'll move to heat. So what is heat? So heat is nothing but the transfer of energy between two objects due to temperature difference. So it can be transferred in various ways. So first one is conduction, then convection, and then radiation. So we'll not go through these processes. They're not important for thermodynamics chemistry. Okay. So the formula that is used for heat, it is QmC delta. So this C here is specified is a heat capacity, M is the mass, and delta T is the temperature change. Now we'll move to next concept, that is delta U. So what is delta U? So from this we get the first law of thermodynamics. Sorry for this confusion. So it is delta U Q plus W. So this is the first law of thermodynamics. So it says that the total energy change in a system is always equals to the work done plus heat exchange. Now why are we calculating this delta U? So we are always calculating the change in any this kind of function, because it is not possible to calculate the absolute value of this delta U. Sorry, internal energy. So we never find out U is equals to what. We'll also always go for this delta U, and this delta U is equals to Q plus W. So here's the question. It says that a gas expands from an initial pressure of 4 atm to a final pressure of 1 atm at a constant volume of 3 liter. If the gas releases 300 joule of energy during this process, calculate the change in internal energy. So it says that a gas is expanding from an initial pressure, that is 4 atm, to a final pressure of 1 atm. And if the gas releases 300 joule of heat, so heat is given. So to calculate the internal energy, so you know that what are things that are given, that is pressure is given, final pressure is given, then we have the volume, then you have the heat released. So the change in internal energy, the formula we know that it is delta U is equals to Q plus W. Sorry. Now since the work done is taking place, the volume is kept constant. So we know that the volume is kept constant, so the work done will be 0. So delta U is equals to heat plus work. Now heat is 0. Sorry, work is 0. So heat will be equals to 300 joule. So delta U is equals to 300 joule. So therefore the total energy is 300 joule. Okay, you can solve this question. I'm giving you the explanation here, so you can do it by yourself also. Now we'll move to the next concept, that is enthalpy. So what is enthalpy? So enthalpy is nothing but the total of internal energy plus PV, or you can say it as more clearly that delta H. So we will also always calculate for this kind of processes the change, the delta, and not the absolute value. So delta H is equals to delta U plus delta PV. Now this delta H is also is equals to QP at constant pressure. So how is it so? We know that delta U is equals to Q plus W. And since pressure is constant, it will be P delta V. Now W is equals to minus P delta V. So this P delta V will cancel out and it will be equals to Q. And that also at constant pressure. So you can, this is just a notation, see both are same. So it is QP. So delta H is equals to QP. Now we'll move to this C. So you have seen in the earlier formula that Q is equals to Cm delta T. Now we know that this C is called as the heat capacity. So what is heat capacity? So if you want to define it, it is simply the temperature that is, so it is simply the, you can say the amount of heat that is required to raise the temperature of a given body by 1 unit. So you can say by 1 Kelvin. So it is that much amount of heat that is required. So it goes by the definition as well, this formula, that it is the heat required that is used to change the temperature per unit, that is per unit temperature change. C. Now that this C can be for various amount of substances. So it can be for 1 mole, so for that concept it is called molar heat capacity. So it is for, if it is for 1 kg, then it is called specific heat capacity. Now we have seen that what is heat capacity and what is this H. Now there is a relation between both of this. You have seen this relation earlier also. So it was like this, that delta H is equals to QP. And if we are considering this QP, so we can QP is equals to, we know that Cp dt and Cp dt. So for 1 mole of gas, we can write it as Cp dt. So suppose we are calculating this H for a small process, that is dH here. Now students, you must often get confused that what is the meaning of this D, this, this and this. So this both are differentiation, but the difference is that we are doing a differentiation such that suppose there is a function like x square plus 2x and you have to differentiate with respect to x. Then we will use this d. And suppose there is a function like this. Now you have to differentiate it. That in that case, you will use this thing. This is called as partial derivation. That means you are differentiating this and keeping this constant like this, and then you are differentiating it. So this is kind of partial one. This is not differentiation, but this is a large change, and whereas this delta is for the small change. Now since this h can be function of anything, so you will use this partial differentiation thing. So if you want to write Cp now, so it will be simply Cp is equals to partial differentiation of h with respect to dt at constant pressure. Now similarly, we have Cv is equals to delta U dt. So if you know that delta U is equals to Q plus W. Now at constant volume, this W will go to 0. This delta U is equals to Q, and we know that delta U is equals to N. So for constant volume, this heat capacity is called at constant volume, that is Cv we are writing. Then we have delta T. Now if we are considering it for a small change, then it will be delta U is equals to N Cv delta T. So for 1 mole, we can write that Cv is equals to delta U by partial differentiation of internal energy with respect to temperature at constant volume. So how we'll use this formula, we will see in the next you can say lecture. So there are two type of formula you are seeing. So if you can see that it can be U is equals to NCV dt delta T, you can say, where in other case we are taking it as Cv is equals to delta U by delta T at constant volume. So this is used for a function. So suppose a process is carrying out such that the internal energy is not varying, you can say in uniform way, but in a way of a function. So for that case, we use not the internal energy, absolute and internal energy, but we are given a function, and then we are said, okay, now you calculate this Cv. So for that case, we use this formula. Now we have the specific heat capacity. So what is the specific heat capacity? So it is nothing but it is the amount of heat that will be required to change the temperature of 1 kg of a substance by 1 degree of 1 degree Celsius or 1 Kelvin. So that heat capacity was for any amount, but it is for specific for 1 kg. Now we have this molar heat capacity. So what is this molar heat capacity? So molar heat capacity is mainly defined for this 1 mole. So if we are saying that, okay, we are calculating the heat capacity for 1 mole of a system, that is the heat required that is used to change the temperature of a body by 1 degree Kelvin, and that body is present in amount of 1 mole, then we call it as molar heat capacity. Now if you want to see the derivation, so this is the derivation that is used to that is very popular for calculating that Cp minus Cv is equals to R. Now for that we use the formulas. So we know that Qb is equals to Cv delta T. Again we have Qp is equals to Cp delta T. Oh, sorry for this. It is right. Sorry. Now if you see for 1 mole, then we know that delta H is equals to delta U plus delta PV. Now if we replace PV by RT, then it is R delta T. Now on putting this value of delta H and delta U from this here, that will be this Cp minus Cv is equals to R. Okay, so that's now for today's class. So we'll cover the rest of the topics in another class. Thank you.